All right, we are recording this for posterity. So welcome everyone to our very first YCRC webinar. We're trying this out, so feedback on how well this works for everyone is greatly appreciated. You should be able to see the screen that I'm sharing with you, which is the presentation that I would have been giving to everyone today if we weren't doing this remotely. And on the title slide for that presentation, there is a bit.ly link that is a link to the presentation. So if you'd like to check it out, it's just Google Slides. So if you'd like to go grab those, save them somewhere, or follow along, feel free to. And then there are, I'm going to be going over 3 examples with some, fairly small data sets, but just the examples that I'll be using today are available on our GitHub site, which is github.com/ycrc, and the repository name is tidying_data.
So Ben, I'm hearing from one of the participants that they can't see the presentation, they can only see you. I see both.
Interesting. What if...
Okay, now I guess you can see it.
I can also just take my... If people don't mind not being able to see my face, I can take the video off, and that should make it clearer to everyone's Zoom that what I want them to see is the slides. So I'm going to do that. I hope no one's offended. And now everyone should definitely see the slides. But please let either the everyone chat or Christine know if you can't see things. So I'm going to get started. The first thing is, if everyone can please, so again, the slides are bit.ly/YCRC-tidy. And if you go there and click on the link on the second slide, you could just fill out your name in there so that we can get an accurate count of who showed up today for our records. It would be greatly appreciated. Sort of go over an outline of what I'm going to cover today. I want to talk about the goals of the presentation, what I want it to be and what I didn't want it to be, a few definitions and some background, description of some of the common operations that we want to use when we're tidying data and once it is tidy, and then 3 examples that I thought would be illustrative. The first of which is an example using Linux command line tools. The second is an example using R and trying to read in a census.gov Excel file. And the third is using Python and pandas to read in some real-time data related to something that I think is on most people's minds. So what I want this to be for everyone is sort of an overview, a few examples of what I think are good practices for tidying data, and trying to put an emphasis on scripting and saving the things that you do to your data so that if you need to start from scratch, you can. You don't always have to use the newest, shiniest thing, and I want to illustrate that with especially with the first example of just using Linux tools that were written in the 70s, the 1970s, and I also am not probably going to have time to go deeply into every single function or tool that I use today, although time allowing, I'm happy to discuss them more deeply. But what I want this to be is more of just like a survey and showing you what some of these tools are capable of, and then from this you can use your Google skills, etc., to actually dive more deeply into the things that would be most helpful to you specifically. So I'm going to pause for a moment and see if anyone would like to uh, either put into the chat or raise their hand with any questions. Okay, cool. So I want to start off with just a definition. And this is sort of a plain English definition of what people who are into relational databases might recognize as different kinds of normal forms of data. But the thing that a lot of people really like about this definition of tidy data is that you can explain it to nearly anyone and they would understand it. And so the definition of tidy data, which Hadley Wickham sort of formulated in his 2014 paper on the subject, is just that each variable in your data forms a column. Let's see if you can, here we go. So each variable here is like, I have a variable A and a variable B and a variable C. And each observation of those variables forms a row. So in this example, I have 3 variables and 3 rows, or 3 observations. And each type of observational unit forms a table. So I might have multiple tables of tidy data, but keeping them as separate but possibly related allows for me to do a couple of nice things. And so why would I want to have my data in tidy form? Well, it makes it a lot easier to manage. You can a lot more simply add and remove, filter, or some more advanced operations to this data. There's been a lot of work at all sort of levels, from hardware up to software, for computers to be able to perform what are called like vectorized, or this in this in this example, it's called SIMD, or single input operations that can be performed all at once. And putting data into this form allows us to not only, more easily and simply manage it, but also oftentimes perform operations on it that can be accelerated and are faster. And the other nice thing is, because it's organized in such a fashion that your variables and your observations are very clearly sort of separated, you can a lot more easily oftentimes find, manage, and filter bad or missing data. And so some of the things you might do to data once it's already tidy is the filtering that I mentioned before. So you can subset based on questions, or remove observations based on some condition, whether it is bad data, outliers that you feel comfortable removing, etc. You can transform your data. So say you measured weight and volume, you can add another variable, such as density, relatively straightforward manner. You can aggregate your data, summing, subtotaling, averaging. All of these things are, again, you're able to do this in a fairly elegant way when your data is tidy. And then you can do things that are relatively simple, like sort it, because you have, each of your variables is a column. some of the more common ways in which data are not tidy, one might call this messy, is you can have columns that are values and not variable names, and I'll go over that in a second. You can also have multiple variables that are stored in a single column. You can have variables that are stored in both rows and columns. You can have multiple types of observational units stored in the same table. You can have a single observational unit that is stored in multiple tables. So you can have like things sort of scattered or condensed in a lot of different ways that make it less tidy. And I want to show you sort of a window into a couple of worlds that will allow you to tidy these things up through these examples in just a minute. But more generally, if sort of like the three most common cases that I encounter are if one of my columns should be more than one column, oops, this isn't right. Hold, please. This should be, oh, no, I'm sorry, that's right. If one of my columns should be more than one column, as in I have rows where I have multiple variables in a single column, the best way to make that tidy is to split that column into multiple columns. And in R, you would use either just the standard library string split, or tidyverse provides a few different ways to take a single column and separate it out into its components. In Python, you could use the string.split function, or pandas exposes this functionality in the series.string.split function. And you can also take a more simplistic approach with some of the Linux command line tools that you can pass in options about how you want the data to be split up, and then they can do so. See any questions that I can answer? Okay, cool. Another way in which you can tidy messy data is when columns should be data in rows. Two of the examples today are actually this, because it's one of the more common things that happen when people either take data that could be tidy and put it into like a matrix or a pivot sort of table. And what you'll oftentimes see is several columns that could all become one. And in this example, there are years that are columns when maybe it would make more sense for this data to be tidy if that all of those columns became part of an observation called year. And the language that people use for this operation is varied. So sometimes it's called melt, sometimes it's called stack, sometimes it's called gather or unpivot or fold. Some examples of functions in R that would do this from the tidyverse would be tidier, the pivot longer, or gather. And in Python, you can use the pandas pivot function to actually unpivot things, and you can use the melt function to do this as well. And finally, occasionally you'll see data where maybe you need things that are in rows to be variables. So in this case, there's a column called type where I think maybe actually what should be happening is I have two variables there, cases and population, that should be columns instead. And so the operation to fix this into tidy data is often called unstacking or unfolding, sometimes cast or spread. In tidyverse, they call this pivot wider or spread, and in pandas, it's called unstacking. This one I find less often, but can be the case. Sometimes if people were collecting categorical data and it turns out that maybe it was collected just a little bit strangely, this can be useful. So before I continue to the first example, are there any sort of general questions about this portion of the presentation? And I will pause for a moment. Okay, great. If things do come up again, feel free to put them in the chat or raise your hand or chat to Christine, and she can help. The first example I want to go over is a real one that I was given from some students at the School of Public Health from a class they had where a professor gave them data for an assignment that was copied and pasted from a PDF where the table was of this form. So you'll see that it has 3 columns, but the table is in, has sort of been hard wrapped so that it fits better for publishing purposes. And the text file looks like this. So they had copied those characters and pasted it into a text file, but it has some problems. So there's space at the start and the end of the lines. There's an inconsistent number of spaces separating each of the pieces of data that we're interested in. And there are actually only 3 columns, but these have 6 columns. And so I want to be able to actually use these data to do analyses, but before I even read them into something, maybe there's a simpler way to sort of fix them and allow them to be tidy. And I'm sure some of you probably could imagine already ways to make this data look better in R or Python. But I enjoy this example because there are some sort of more advanced ways of using the Unix shell and Unix tools to fix these. And that's what I'm going to show you how to do. So briefly, the things that we need to do to this data to make it tidy so that we can actually begin to analyze it are we need to split each line into columns or fields. We want to take the first 3 columns and sort of drop them on top of or concatenate them to the next 3 columns. I want to, so that my favorite data analysis program can read this in more easily, I want to separate these fields instead by commas rather than spaces and make them single commas. And I also want to ignore those empty lines. And finally, I want to add column labels so that when I read these data in, I understand what they are. And so before I show you some of the ways in which I would do this, I want to give you a brief survey of some of the tools that you would find helpful in manipulating this text file. So the first one is the command called tr for translate. And the example I have here will take a file that is directed to it. Let's see. Can people see my cursor when I move it in front? Okay, cool. So if I wanted to do something to this file that's called file.txt, I can redirect it with this symbol to the translate command. The -s option means I want to take every instance of space, as many of them as there are, and collapse each time I have one or more of those into a single comma. And so this you can imagine will get us like kind of the way there. I'll show you how you might use that in concert with some of these other commands in a second. Cut is another useful command. It is simpler than some of the more advanced things that are actually windows into their own languages. But it's really nice if you just have some column data that you want to extract from. And what cut does is it takes data separated by some delimiter, and you can extract columns from it. So here I'm asking cut to operate on some file called file.csv. I'm saying the delimiter with -d is a comma. And I'm also asking cut to skip lines that don't have delimiters on them. So here's another way I could skip empty lines. And the final option I'm giving it is the -f or fields. So here I'm asking to operate on the 2nd through 4th fields. So this is also nice because I can specify a range of fields that I want. So if you have a really wide table of data that you want to extract fields from, this is a really elegant way to get like the 3rd through the 1000th column. And the nice thing about all of these commands that I'm showing you is that they operate on files line by line. So if this file is, 3 kilobytes or 10 terabytes, this, the 10 terabyte one will take longer, but I can run it on a computer that doesn't have, enormous amounts of memory, where I'm sure if any of you have tried to use big data sets in R, that can oftentimes be a problem because R likes to read the entire file into memory in order to do things to it. Another useful command is T, and it's meant to be, saying the letter T, and that is the shape that is trying to emulate. So it's a way to take the input from one command and sort of split it off into other places. And if you're familiar with Linux and Unix pipelines, this can be useful, and oftentimes it's just used as a way to take output that you're redirecting somewhere else to also save it to a file. But what you can do, and one of the examples I'll show, is you can also use it to take output and split it to multiple other inputs. And with this syntax here, I am taking output from whatever T is getting and actually sending the same output to 2 different streams here. Again, it'll make more sense in a minute. And then these last 3 you probably have heard of. Sed is just what's called a text stream editor. This example here, I'm using sed to perform a regular expression filter on a file.txt. And what this thing says, even though it's kind of hideous, is take any file that's just empty white space and skip it. And what this expression is actually saying is match some number of characters where starting at the very beginning of the line, that's this caret here, 0 or more white space characters all the way to the end. So I'm saying anything with just white space and no other kinds of characters, just delete that. This next tool, grep, is a text search tool. You can often use it to find patterns in files or streams of text. And here, I'm doing sort of the equivalent to this sed command. I'm asking grep to search for all non-white space characters and print those. And so this would be sort of the opposite way of saying if each line in this file has anything but white space, print it. Awk is another command that is very useful. It's a command that implements an entire domain-specific text processing language. Oftentimes, you'll see it on Stack Overflow or other places on the internet, just implemented as little one-line, very terse commands, but you can actually write scripts in awk. This has sort of fallen out of favor because there are easier to program and easier to read languages now, like Python and R, that you can get more things done with and more people understand. But awk is really nice because it does the right thing often with tabular data. And so I'll show you that in a minute. But what this sort of obtuse little awk command does is it prints only lines from file.txt that have the number of fields as the very first line. And so this is a tricky way of skipping all of the empty lines as long as the first line has the right number of fields that you're interested in. So nf is a special variable in awk that is number of fields. Okay, deep breath. Are there any questions about this slide? It's a lot, but I sort of wanted it to almost be like a little tiny flavor of a cheat sheet for everyone. Okay, so I'm going to continue to what I called solution 1 for this example. I'm going to walk you through this. Both of these, so I have solution 1 and solution 2. Both of these are available on the GitHub page as scripts. Let me just, I can flip over to there. So here, this example 1 I called Linux Toxo. And in here, I have the 2 examples, an image of the original table and the problematic data here, so that you can see it in all of its glory. I'm going to flip back here to the presentation real quick. So what I'm doing here is I'm executing 2 lines. The first one is a bit of a pipeline, and the second one adds the header to our file, but I'll walk us through it. So I'm going to start here at this awk command. So I'm asking awk to treat all of its output as comma separated. So OFS means output field separator. And then I'm saying, please print as long as there are more than one field detected. So this is another way to sort of skip empty lines. I'm saying, please print the first, the second, and the third column from the file called toxoplasmosis.txt. And the thing to remember about awk is it starts counting at 1. So this is the first column. And in this case, awk is smart enough to skip the empty space at the front of those lines. And so I can do this in order to get those first 3 columns, and then I can run that same command again to get the second 3 columns. And with the magic of subshells and redirection, what I can do is ask the cat command or concatenate. I can say stack the output of this first command on top of the output from the second command. And this final part here of this really long command is telling the shell to redirect all the output from cat to a file called toxoplasmosis_fixed.txt. And so once I do that, I'll have comma-separated output of what I want, but the only thing that's missing is I don't have a header for my data. And so I can use sed to be kind of tricky and add something just to the very top of a file with this expression here, where I say match the very beginning of the very first line and replace that with a brand new line that is my header that I want. So cases, comma, number tested, comma, rainfall, and this /n means a new line character. And so what I'm doing is I'm just matching the beginning of the file and replacing the beginning of the file with a new line. And with this -i option, I'm asking for it to happen in place. I think sometimes if you're on a Mac, you might have to specify a file extension that would be the backup file for this. So that might end up looking like sed-i and then a space and then .bak for backup, oftentimes is what people put. But what I'm telling here is I just want the new thing to overwrite the old thing. And so this same file now should have the right header. And I'm going to pause again and ask if anyone has any questions about this first solution. So what is this? Sometimes people call it the caret, this symbol that looks like a greater or less than symbol that's pointing up. And in regular expressions, this oftentimes means match the beginning of a line. And it's a good way to anchor something that you're searching for at the start of a line. And so matching just that character actually just means match the very beginning of a line. So this would also be a way, you can use this character as the only thing you're matching to insert something at the beginning of every line of a file. Good question. I have, at the very end of this presentation, some useful links, and 2 of them are websites that allow you to play around with regular expressions sort of interactively, where you can paste some text and then test out different regular expressions. They can be very powerful. They also have been the reasons why the entire internet slows down. So I tend to try and use just about as simple as I can of a regular expression. And if things get too complicated, I tend to try and write a more full-blown script to handle that situation. But oftentimes they're like puzzles. Let's see, the other question is, what is the difference between the forwards and the backwards slashes? So for sed, these forward slashes are used to separate different parts of this regular expression match. And so here I'm asking SED to do this substitution only one time. And this first slash means now I'm going to tell you the thing to search for, which is the first line. I'm sorry, which is the beginning of a line. So this is the beginning of the line for the first line of the file. And the thing that follows that slash is what I want to replace it with. And then this final slash tells SED that I'm finished telling it what I want to replace with. And so here the slashes are just separators between things I'm telling SED about. And the other slash, these backslashes very oftentimes are used as what are called escape characters. So here I'm saying to SED, this in, don't actually print the character in. I'm escaping the letter in to mean a brand new line. And if you just search for escape character SED, there'll be a list of those. Slash in is a fair, or backslash in is a fairly universal way of saying I want to print what would happen if I was in a text editor and I hit the return or enter key. You'll see this in R and Python and other programming languages as well. And then these two slashes up here are, I'm doing something kind of similar. I'm saying I'm making a new line here. So in my text editor, I hit backslash and then the return key or the enter key. But I'm telling the program that's interpreting this script, bash in this case, to ignore the following character and just treat it like normal white space. And the reason that that was nice in this case is that the command that I'm running, actually starts at this C from cat and goes all the way to this T at the end of this text file. But it's hard to look at on the screen because it'll sort of like fly off the end. And so it's just a way of me wrapping a very long command in such a way that it's easier for my eyes to see it. Does that answer that question? Excellent. I'm going to show you a second solution that has just one problem with it. Which is that it doesn't guarantee the order of the data. So the nice thing about solution one is that I will replicate the data in the original table in the exact order that it's portrayed in that image. And so sometimes there's information embedded in the order of the observations that you have in your data. But if that's not true, if you don't care about the order of your data, sometimes that allows you to be a little bit messier. And so what I'm doing here is I'm using that translate command to take our file of interest and squeeze with this -s all occurrences of one or more spaces and replace them with a comma. And I'm taking that output and redirecting it with this pipe character to T, which I'm splitting into two cut commands. And those two commands are taking the input from TR, and I'm telling cut these lines are comma separated, and this -s means skip lines that don't have any commas on them. And then I'm doing something kind of similar to the previous example. I'm saying, take the first 3 columns. In this case, cut doesn't know about, skipping the very first empty column. So if you guys are interested, I can run sort of components of this so you can see what the outputs are. But I have to skip the very first column because it's the empty one, and just take 2 through 4 and 5 through 7. And in similar to the solution one, output those 2 columns separately, and then pipe those 2 things through that same sed command. So add our header, and sort of in one very hideous command, fix this piece of data. And so the nice thing is that this happens in a single command rather than in 2 lines. And the cut command is a lot faster than awk, because awk is a whole programming language, and cut is meant to be very efficient at just extracting fields from text. And so I think on my laptop, again, this happened so fast that I couldn't perceive a difference in time. But on my laptop, on this very small file, solution 2 was about twice as fast. So if this file were many gigabytes, maybe that would be fun. Then maybe this would be the more desirable one, as long as the order isn't guaranteed, because T doesn't really guarantee the order of which it output from this and this subshell. And so this is sort of like a slightly more brittle solution to the same problem. I'm gonna pause here again and ask if there are any questions about this zany solution. Okay, I will now move on to example number 2, which is my R example. And what I wanted to do is just go grab a piece of data from census.gov. They periodically release per state and region estimates of population, in between the times when the census actually happens, which is exciting if you care about these sorts of data, because it's happening very, very soon. And so let me actually go. So I just run over to census.gov, and the Excel file that I downloaded is in the repository, but I believe it is this one here. So monthly population estimates for the United States, April 1st to December 1st. And it's less than a megabyte. It's nice and small. And so people spend a lot of time writing really cool packages for R. One of them is called Read Excel, which is meant to interact with Excel files. You might recognize, if you're old enough, poor Clippy and its icon. And then it works well with the rest of the tidyverse packages, which I don't have time to go over all of them today, but just to sort of call attention to them, as these are the core tidyverse packages that get loaded when you when you run the command library tidyverse. And read Excel is sort of part of the extended tidyverse. You have to load it separately. So I can load the read Excel package into my library. And then one would be tempted to just run the read Excel function on this Excel file, and then wishfully hope that this just reads in those data in a way in which I can then start to do analysis on them. But when I try and do that, I get this perplexing error where it says, I made new names for your columns, and they're called dot dot 2 and dot dot 3 and dot dot blah, blah, blah. And there are 7 more problems. So it's not an exciting thing to see. And if I look at my my census tibble or data frame, like object, I'll see that it is a table with rows something or other, and then the columns are named that weird thing, and then there's row called table1.annual, and it's a bunch of NAs, and then geographic area with just one, and then this column has probably population or something. And so it just looked really messy, and a lot of things got parsed as characters, so they wouldn't be easy to understand as numbers, and so on and so forth. And so what I recommend doing, if you hadn't already, is going back and looking at the Excel file itself. So I have just some screenshots here. Taking a look at this Excel file, it has a lot of cells in it that are not column headers. So if I look here, it looks like the actual headers start at row 4, and I could probably just throw out the rest of this stuff. And if I wanted to refer back to the human annotations for these data, I could go back to the original Excel file. And then if I go look at the bottom of the file, we'll also see that the bottom has extra annotations for, again, for humans that are meaningful, but not great for me if I just want numbers in a table. And so, also, just pretend like you looked at the other end of these data and saw which column they go out to. So after I've looked at my Excel file, and I understand sort of the subset of the cells from that file that I would like to read, I can go back to my read Excel function and pass to it a range. And this range, I think there are ways that you can ask for non-consecutive portions of an Excel file, but in this relatively simple example, I'm asking for sort of the space bounded by the top left cell being A4 and the bottom right cell being M62. And so the data go out to column M and down to row 62, and they start at row 4, column A. So just to review. So I want to start right here, and I want to go down to the 62nd row and out to the very last column in this file, which is M. And so I get a lot further with this. I see that I'm parsing in numbers as numbers, so they're cast as what are called doubles. And so tidyverse is saying, I know all these are numbers. Some of them I'm expressing as scientific notation, but that's okay. But I have a problem now because I have a bunch of columns for each of the years. And it makes it difficult for me to do some analyses or modeling that I want to do, because that would be a really excellent part of my observation rather than as columns. And so what do I need to do to make this tidier? Oh, sorry. I also want to, because this very first A4 is actually a merge cell, Read Excel got a little upset about it, and so just threw up its hands and said, this looks like a blank cell to me because of the way it was merged. So it ended up being parsed as ... 1, which is not a very meaningful variable name. So I want to rename that very first column. And then I want to maybe take all of the columns that are years and move them to a column called year. And so does anyone remember or want to look one slide ahead to how I would take all of those different columns and put them into a single variable or column called year? All right, well, time's up, and I'm going to show you how I would do it. The pertinent command to just do the function I was talking about is this gather command from tidyverse. And what I'm saying here is gather all the columns starting at 2010 out to 2019 and use gather them into a column called year and put the values that they were representing into a column called population estimate. And so I'll go over the rest of this in a second, but I can get pretty far tidying this up so that I get a table where it tells me the region, the year, and population estimates for both these regions and the states. And I find this data in this format to be a lot more useful for plotting things, for joining to other pieces of data that I might be interested in, rather than that big matrix, which is maybe easier to search with my eyes. The big matrix is almost like the simplest form of data visualization. I want to go over the rest of all of this solution because, again, it's sort of a lot of stuff packed into one place. And I did this on purpose to sort of give you a flavor for what a real solution would look like, and also to give you some sort of jumping off points for things to search for in your own analyses. So this first thing I'm doing is I'm taking the Excel file that I read in with just that subset range. So I'm taking this hunk of data right here, and the first thing I'm doing to it is I'm renaming this column called ... 1 to region. And tidyverse has this fancy operator that they added that, shoot, I forget the original package that made this up, but you can think of it the same way as the vertical line or pipes from Unix. So it's saying, take the output from the thing on the left of me and use it as input for the function on the right of me. And they're saying, take all of the data in the table called census underscore XLSX and use it as input for the function called rename. So I want to take those data and rename the column called ... 1 to region. But I'm not done yet. So I have another pipe that says drop any rows where there's an A. And that, yes.
We have a question.
We have a question.
In R, when do you use the single quote? And when do you use the double quote?
So in both R and Python, you can use them interchangeably as long as they enclose a string that you would like to enclose with the same characters. I think there might be some exceptions in R, but I can't think of them off the top of my head. So I could specify this string called census with a quote the actual quote characters or the apostrophe or single quote characters, which I usually call them. And as long as I use the same character on either side of this, R doesn't care. The nice thing about this is in both R and Python, it allows you to use the quote character you aren't using inside the string. So I could put an apostrophe somewhere in this string if I wanted, or vice versa. If I wanted to put a double quote character into the string, I could use the single quote or apostrophe on the outside. Good question. So where was I? So I'm dropping all of the rows with NAs in them. This is a good way to get rid of empty rows or parts of the matrix that weren't well defined. I invite you to try running this without that and see what rows pop up with NAs and maybe why that happened. The next is the select function. And what I'm asking here is to give me the inverse of the two-column census and estimates base. And what this line is doing is it's saying, take those two columns out of my data. So I'm just throwing out this part and this part because all I'm interested in are the yearly estimates for each of the regions. And so it's sort of a wacky way, but the tidyverse way of saying, take these two columns and throw them out. So that's another part I'm doing. And then this gather function, what I discussed previously, is take all of the columns starting from 2010 out to 2019 and treat the column name as a key and its value rename to population estimate and gather them into this tidy format. And this very last part, I'm taking year, and because it was originally, parsed as a column name, tidyverse or R will treat it as a string. And so if I wanted to treat it like a number, I need to, what the tidy folk would call, mutate it. So here I'm saying, take the column I've named year, which was in this previous line, and actually return a new column where year has been cast as an integer. And so here, now this is a number that I can sort more reasonably rather than a string of characters that are the same thing. Whew. So that's my R example. Are there any questions about that? Would anyone like for me to run all or some of this example in our studio so they could see it happen live? Sure, okay. All right, now is when everything falls apart. No, okay, so I'm gonna start up our studio for myself. I'm gonna go into my R census directory. Let's see, I'm gonna set this as my working directory. I'm gonna open my R file. And I'm going to load tidyverse and read Excel. What did I do wrong? Oh, I'll load them separately. R is not my first programming language I usually reach for. So let me do this real quick. And I will fix that. later. Okay, so I loaded those 2 packages into my library. I'm not sure there's a great way for me to make this larger. I wonder if I just do, oh my God, how do I make it like bigger than this? Hopefully that's a little bit better for folks. Pull this over a bit more. So here's my line where I load in just the range that I'm interested in from this file. And again, there's that first column that doesn't look great. So if I just type census XLX, you'll see not so happy with that. You'll see that we have data for all the years, and then we have some columns that I wasn't originally interested in. In our studio, you can also look at the tidyverse version of data frames called tibbles, the same way as you would a data frame. You can sort of look at it in a more Excel-like view here, and then you can filter things, etc., from here if you were so inclined. So I can just show you different portions of this pipeline. So say I just want to do this in steps, I could maybe just do this. Now I see step 1. Looks almost the same, but now my column is renamed to region. So I like that. Let's see. You see this empty line between Wyoming and Puerto Rico because, it's not a state, but they kind of treat it like one. I can drop that with this drop in A function. I do step 1. Drop in A. And oops. Step 2. If I look at the bottom of step 2, I don't have that empty line anymore. So then if I take step 2 and pipe it through this select function into step 3, now in step 3, I have a very similar table, but just without those 2 columns that I don't care about for the purposes of my tidy data frame or tidy tibble. And then what step am I on again? I'm on step 3. So step 4 is the gather step. In this example, where I take step 3, oops, that won't work. Step 3 and pipe that through this gather function. So here it almost looks tidy enough, but the year is a character type. And so if I try and sort on year, it might not do the right thing. the last thing I do, step 5, is take step 4 and mutate the year. Oops. So there we have the whole thing separated out into steps. And one of the really nice things about, I mean, even if in me troubleshooting how to do this, and when I was developing that, one big long command, I did run them separately as I showed. The really nice thing about those pipes is that R won't keep around separate objects that take up a bunch of memory for any of the intermediate steps, like I just did when I defined each of the intermediate steps as separate objects. So you'll see over in the RStudio environment pane here, I have how many copies of the exact same data, each of which is taking up like some footprint in memory. And in this small example, it doesn't matter because the data are so small, but if you're working on data of any size, this can add up a lot. And so the really nice thing about those pipes is they work conceptually similarly to pipes in Unix, where I'm asking R to only create like enough intermediate to execute all of these things, but what I really care about is the final result. And so I don't end up with permanent copies of all of these intermediate things that I don't care about. That's sort of the power of these pipes in concert with all of these different tidyverse functions. So that's the R example. Any additional questions about that? If not, I can move on to the Python. All right, so I'm going to move on to example number 3, which is, oops, let me go back to the actual slides. Here we go. Example number 3. Ripped from the headlines. Say you wanted to take some COVID-19 data and analyze it yourself. There's a GitHub repository that's been updated, I forget, every 3 hours over the past so many days. Sort of tracking confirmed cases, recovered cases, and deaths in this pandemic for the SARS-CoV-2 virus that causes COVID-19. And the folks who are maintaining this have a really pretty actually, can I, oops. Well, if you go to this GitHub page, they have a link to a really pretty dashboard that they made that has like points on the map proportional to the number of cases and a lot of other stuff. But if you just wanted to take a look at the raw data, if you had questions about what they're using to make that dashboard happen, maybe you would want to use Python for this. And so I'm going to show you how to use Python and pandas, and when we should have time, I'll show you sort of interactively how to run the example in Jupyter and take the data that they have, again, sort of in a non-tidy form and convert it to the tidy way of thinking about these things. And so this might be reminiscent of the census data. or after parsing, I get these columns that are dates that maybe should be observations instead. But here's my Python code, so I can import pandas as PD, which is sort of like the convention, so that you don't have to type pandas dot for every pandas function you'd like to run. And I'm storing, pardon that. I'm storing the URL that points at the CSV file for confirmed cases as a time series CSV file. And I can actually have pandas read a CSV from the internet. So I can just get the most up-to-date version of this data and store that in a pandas data frame called confirmed. And what that looks like when I first read it in is this data frame is indexed from 0 on, and it has several columns. One is called province/state, another country region. It has latitude and longitude data in it, and then there are a bunch of columns, each of which is a day. And again, this is data in a form that is maybe a little bit easier for humans to read because it's not, thousands of lines long, but it's in a form of what I would call it's sparse in that not every cell has meaningful data in it. So you'll see here down on the 5th line or the index 4, there were actually 0 confirmed cases in this place in China on this day, but because this matrix has to have cells at every row and every column, there's actually a 0 there, as opposed to if this data were tidy, we wouldn't have to store that information. So what I want to do is take these data where the days are and do a similar transformation to gather that I did with R, but take here we go. Take the dates and put them into a date column, and then take all the cells from that matrix and make that like, I called it patients, or just the count of confirmed cases, and make that a separate column. And again, because this matrix is sparse, there are many observations of 0 that maybe I don't care about. I can drop all of those out of my data frame that I want to do analysis with. That'll make my data frame smaller. It'll also make any functions I call in it happen faster. And then finally, I'll convert the date column to a date data type, which Pandas is pretty good at understanding dates. And when I show you interactively how to run this, I'll show you a neat little trick with those. So the first thing I do here is call the pandas melt function. And what melt wants to know is what are the columns that it calls ID variables, or the things that you want to keep as columns that, and so I'm just taking the first 4 here. I'm sorry, yeah, the first 4. So this slice, or this way of indexing the columns from the confirmed data frame says, starting at the very first thing, go up to, but not including the thing indexed at 4, which is the 5th thing. So the first 4 columns, so look back here, are 1, 2, 3, 4. So in my gathered or melted data frame, I'll have observations for each of these things, and then I should also get a date where I have these days, and then a patient column, which I specify here. So I want the var name is what pandas call it to be date, and the value name, or the values collected for those variables, as patients. You could also call this confirmed cases if you wanted to. And then on this next line, I am developing what pandas calls a mask. So, and when I show you this in Jupyter, this might make a little bit more sense, but what I'm sort of pre-calculating is the places in my new data frame where the column patients is not equal to 0. So this will return true for all rows where patients is not equal to 0. But then I also want to combine that logically with all the rows that are not NA. And for, this data is not perfect. It's sort of always being new data being thrown in, and so sometimes there's a 0 there, and sometimes there's actually an empty cell. And so I just want to toss both of those cases at the same time. So what this ends up generating is a mask, which I can use as an index to my data frame. And here I'm just sort of with this defining the data frame as that data frame where only rows that satisfy my mask are kept. So I'm sort of tossing out rows where either of these two conditions is not true. And then I am casting or converting the date column to a date time data type, which makes it easier. So I could have just made this into a number. It's a little bit trickier because those text strings are, have slashes in them. But it makes it easier to sort when I convert this into a date time. And so Pandas understands how to take those strings of text that are, month/day/year and convert them into a richer data type that understands dates. And so that's what I'm doing on this line. And after performing those 4 lines, I get a data frame that looks like this. So I have those original 4 pieces of information, but now I have each of these rows is an observation by day, where the confirmed cases or patients is its own column, and the dates are formatted and a special kind of data type that I can do some interesting indexing with. Questions about that before I hop into Jupyter and sort of run some of these live? Okay. Jump over to my Jupyter session, and I'm gonna hop into the 3rd example directory, and I'm gonna open this IPython notebook. And just gonna make sure in Pandas is installed. Okay, cool. And I'm going to load Pandas. And here is my URL for the CSV that has the confirmed cases stored in it. If I do that, that should be relatively fast. And then here, I'm going to read that file from the internet, and you'll see that we have some new cases. I guess the most recent one they put in was in Newcastle, Delaware. And so you'll notice here, like I said before, that there are lots of columns that I don't want as columns. I want those to be my part of my observations. And so here I'm also just showing that the confirmed data frame has an attribute that is the columns is a list. So I can see if I just refer to columns, square brackets, :4. I'm talking about these first 4 columns. And what that 4 means is up to, but not including the index 4 of that list. And Python starts counting at 0. So index 4 would actually be the 5th thing. Is this big enough, or can I? I'll probably, let's see. Shoot, Mac keyboard. That's probably a bit better. Can I go one more? Sure. All right. So just showing off my index there. And so this is falling off the edge here, but here's my melt command, my melt function, where I'm saying use these columns as the identification variables and treat all other columns as the things I want to melt into the variable called date with values called patients. And so I'm taking all of those different columns and putting them into these 2. And here I'm just asking about we have a question about masking and filtering. I will, yes, let's do. So the question is, so masking is the way to filter data in Python. It's one of the ways to filter data in Python. It tends to be a really fast way because the operations that Python is running underneath are quite efficient. So let's see, if I insert, sure, it's fine here. So if I were just to run, this already ran, so it's hard to do. But if I take a look at drop mask. Oh, I didn't run this yet. So let me run this and run this. So that should say some things. Oops. So this drop mask line here, where I ask to combine basically these 2 logical statements for all of the rows in the patients column. What I'm generating is a special kind of data frame that just says true, 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 false, false, blah, 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 blah. And where each row will be filtered or not based on the logical statement that I constructed in that mask. And this allows Python to really fast toss out rows that I don't want. And by sort of saving all of that logic ahead of time, it can be a lot faster. A different way of doing this, I believe I put in here. Oh, it's further down. So there's a common criticism of these constructing these masks is they're quite verbose. So every time I'm talking about the patients column, I have to say where that patients column is. So it's in this data frame. And so it's a bit slower, but if your data are small enough, you can use the query function where you pass just a string that is logic where you refer to the columns as just bare strings here. I'll go over that in a second. But this would be sort of a different way of filtering things without using a mask. But masks are great. Masks are fast as long as you understand how to use them. So you can combine with the single ampersand or the single pipe for and or multiple masks. And so pre-calculate that and then filter your data with that. That's a very common way of filtering pandas data frames. so where am I? I'm here, I think. So now I just want to take the date column and convert it to, oops, convert it to a date time. And the neat thing that that allows me to do is to create a mask where I'm indexing on dates. So I can ask about just the cases that happened this month by asking for rows in this column, date, that are greater than March 1st, but less than March 31st. So if I can construct that mask and index on that mask, I get probably a different answer. Oh, gotta make the mask. This is why I'm not a huge fan of Jupyter Notebooks, to make it really easy to execute your code out of order. But here we go. So there are 2,201 observations in this data frame that were between those two dates. And so you can see here, here's some on the 2nd, and here's some on the 11th. And I can sort of combine that with also asking about, here's another way that you could filter. If you wanted to filter on this text-based column, if you wanted to just see cases in New York, I can run this. So I can see, many new confirmed cases in New York and New York County. What is this today, the 11th? Yesterday?
Yesterday.
So yesterday there were, several rows added for that. And so this is sort of a way that I could filter based on a string kind of data. So those are my 3 examples. Again, they're available at our GitHub page as the tidying_data repository. There's a link to this repository at the beginning of the lecture, which is available at bit.ly/ycrc-tidy. I just wanted to close out with some useful links for the 3 examples that I showed today. So if you want to test out some sed, awk, or grep commands, there's a guy who wrote JavaScript front ends for these that you can paste text into and try your sed command out on maybe just a sample of your data. If you don't want to be running that on, or don't have access to a computer where sed is going to run the way that you want, or awk or grep. These 2 websites here, regex 101 or regexr, are great sort of playgrounds for you to test out regular expressions to your wildest dreams. And they have like a free-form text window where you can paste text that you would like to use as an example or a sample. Our studio maintains some really nice cheat sheets, which are usually like if you printed a front and back landscape page that has a bunch of functions for the various tidyverse packages and descriptions of them, and also pretty pictures of sort of what kinds of function, what they perform. There's a R for Data Science book that is available online for free. And sort of the most pertinent part of it for this presentation is the Transforming Data chapter. So here's a link to that. And there's also, I believe it's still being written, but there's a modern dive into R book that is available online for free right now. And the sort of the wrangling chapter would be a good place to go learn more about how to use different R functions to do the kinds of things that I showed you today. And then for Python and Pandas, Pandas has an excellent, so Pandas is a little bit younger than the tidyverse. And so oftentimes people want to know, well, okay, so I would do this way with a tidy function. How would I do that in Pandas? So they have sort of a guide under their Getting Started section for comparing some of the Pandas functions with R functions that you would perform. And then they also have a guide for how to reshape data, thinking about it the way Pandas want you to think. And finally, they just have a nice little cookbook section with sort of, here are some things that you might, some common tasks you might want to be able to perform. And here's how the authors of Pandas would perform those tasks. And so finally, I want to say thank you, everyone, for digitally showing up and for your patience. This is my and our first time giving this sort of a webinar. If you can take a look at the slides, the Google slides, go to this website and fill out the survey on how we did and how we can do this better. We would really appreciate it. And with that, oh, and Christine also posted that link to the chat. With that, I just want to thank everyone for showing up, and I will sort of keep this open for a while if people want to stick around for sort of Q&A. We do have a few minutes left. But other than that, thank you for coming, and you are released. You can leave as you please. And Christine will send a follow-up email with a recording for this lecture. Hooray! Right. All right, everyone. Looks like the folks who have left all said thank you and didn't have any questions. I'm going to have one final call for any additional questions or feedback. And after that, I'm going to sign off and wish everyone an excellent day. All right. Well, thank you everyone for attending, and hope you come back.